Welcome! In this video we will guide you through the measurement and data processing workflow for EMILIE, our groundbreaking nanomechanical analyzer. If you're unfamiliar with sample preparation or general chip handling, we recommend watching our Introduction to Sample Collection and Handling video first. Before beginning, ensure that an EMILIE chip is already loaded into the vacuum chamber and operating under stable vacuum conditions. In case of operating with a PHILHAR high-pace Neo pump, a stable vacuum is reached when the membrane and turbopump operate below 10 watts. For instructions on chip loading and vacuum setup, refer to section 7.2 of our user manual Standard Measurement Procedure. This demonstration uses PHILHarmonics version 1.0.5, OPUS version 8.7.41 and 9.1.4, and an EMILIE validation chip loaded to the setup. To begin, install PHILHarmonics, the operational software for EMILIE and PHIL. You can download it from the Invisible Light Lab resource hub and follow the installation steps. Once installed, launch PHILHarmonics. On startup, the software will automatically check for updates to ensure your firmware, software and presets are up to date. Navigate to the EMILIE tab in the top menu. From the first drop-down menu, select the appropriate preset. Presets with the prefix ELLabs are optimized for the respective chip batches. To create custom settings, select Current Parameters from the drop-down and click Make New. For this demonstration, we select the preset for the EMILIE validation chip and click Apply. After applying the preset, you may also enable Auto Apply Parameters. This feature will automatically identify the optimal resonance frequency, apply the corresponding tracking parameters, and display the final operational plot. Alternatively, you can also manually select the resonance frequency from the frequency finder in the drop-down menu and click Continue to apply parameters. In the Results section, you can now monitor the tracked resonance frequency and the corresponding analog output signal to the spectrometer. Use the plot legend to toggle between the views. Ensure the temperature controller is active and stable. This is indicated by a green background of the temperature monitor on the bottom right. Further, ensure the resonance frequency of the membrane is sufficiently actuated, which is indicated by the color of the RMS value placed centrally under the frequency plot. Red indicates an input overflow, meaning the actuation is too strong and needs to be reduced. To adjust the drive, navigate to the drive setting in the top left and open the drop-down menu. Enter a new value, paying attention to the sign of the amplitude. Both negative and positive amplitudes are possible. The new value can be applied by pressing Enter. A yellow RMS value indicates an insufficient drive amplitude, leading to an unstable frequency tracking of the membrane. Therefore, choose a value that results in a green RMS value. An optimal RMS value is typically between 100 mV to 400 mV. As a next step, switch the plot to display the analog output to the spectrometer. When no measurement is running, a properly set offset should bring the DAC close to 0. Ensure that the output range accommodates your signal. The analog output must remain within plus to minus 3 volt. The default range of 2440 Hz is typically suitable. If changes occur, for instance by a drifting frequency or optical changes like the aperture or the beam splitter, adjust the offset or rerun the EMILIE tab. Once all values are within the range and stable, EMILIE and PHILHarmonics are now ready to operate with the spectrometer. Open OPUS and navigate to the Step Scan Modulation menu. For first-time users or unknown samples, we recommend starting with one of the predefined EMILIE presets available at invisibleLightLabs.com. The presets are designed to cover the mid-infrared range from 4000 to 400 wave numbers with a resolution of 4 wave numbers, indicate an estimate acquisition time and the signal quality, where LQ, SQ and HQ stand for low, standard and high quality. Due to the thermal response time of the EMILIE chip, we typically recommend a stabilization delay of 30 milliseconds, 200 coadditions for noise reduction, and an aperture of 6 mm to ensure uniform illumination. Click Start Step Scan Modulation to begin the measurement. During step scan modulation, you may observe the modulation directly in PHILLharmonics via the frequency and DAC plot in the Result tab. If the FTIR central burst causes a modulation of more than plus or minus 3 volts, PHILLharmonics will display an output overrange warning. If triggered, increase the output range in the drop-down menu at the bottom right and restart the scan. Notice, any adjustments made in PHILLharmonics during a step scan will invalidate the spectrum. Always abort and restart the step scan after making changes. After the scan is completed, you will see the raw NEMS-FTIR spectrum. This spectrum typically includes the intrinsic absorption of the EMILIE chip material with a maximum around 840 wave numbers. As for the presented case of the validation chip, one can further see the vibrational features from the 10 nanogram polystyrene beads. For data post-processing, one can use the EMILIE data processing macro directly in OPUS. To process a NEMS-FTIR spectrum, a background spectrum of the FTIR light source recorded by an EMILIE light chip and also a blank spectrum are required. In the following example, we will execute the macro based on pre-recorded spectra featuring 40 nanograms of polystyrene beads. Open the macro menu and select Run Macro. Navigate to the EMILIE data processing macro. Drag and drop each spectrum into the corresponding field of the macro. The EMILIE default value is related to the signal processing of NEMS-FTIR spectra and based on several factors, such as illumination and sample distribution. The preset value of 0.695 assumes full illumination of the EMILIE chip and even distribution of the analyte over the perforated area. For more information on the theory behind the processing, visit our data processing guide available online at invisibleLightLabs.com. Execution of the macro will apply a background correction, blank subtraction, and signal conversion to the common absorption units. As a result, a new file with the suffix processed will appear in the same file directory. For spectrometers operated with OPUS version 9.1.4 or newer, follow the same steps as described and demonstrated for version 8.7. If using an Invenio spectrometer, ensure that a firmware version of 1.6 or later is installed. After acquisition, open the resulting 3D file. Right-click on the spectrum and select Extract File to get a 2D spectrum. Like with former versions of OPUS, the raw spectra can be post-processed using the EMILIE data processing macro. Open the macro and drag and drop each spectrum to the corresponding field. The resulting post-processed spectrum will then be displayed in OPUS and also saved individually under the same file location with the file name and the suffix processed. For more detailed instructions on the measurement procedure and data processing, please visit our resources hub at invisibleLightLabs.com. Thank you for watching.